So this is where I normally show some videos about manufacturing processes, and I may do that. I'm trying not maybe not show as many as I normally do, but I think it's important that you have some understanding of basic manufacturing processes, because those manufacturing processes really drive what's on the technical drawings for those parts that are made with those processes. So, whether the part is cast in place or machined may have variations of different types of informations that is on the drawing. So those manufacturing processes are important. We've hit preferred fits, just a little review about fits. There's three types of fits. What are they? Yep. Interference. That middle.
Transitional.
What's that?
Transition.
Yeah, transition. Yeah.
So one fits, one doesn't.
One's got space, one has no space, and one could have space. Yeah. So good about that. And then surface control, and then our introduction to geometric tolerancing this week. So that's a pretty big
Surface control, the little triangle.
yeah. Yeah. Like Noah said, the surface control are the little check mark triangle looking things we've seen that y'all have asked me about. And I said, don't worry about that right now. All right. So that statement is no longer valid. We're worrying about it from this point forward. All right, all the way forward. So some of the basic manufacturing processes about reforming material. So we're changing the shape of the material by casting. What does anybody know about casting?
Like, they could be like melting metal down, pouring it into a cast to make it turn off.
Yeah, so you take a material, whether it's melted, metal, plastic, whatever, you melt it and you put it in a cavity and it hardens, cools and hardens, and you have some different shape, right? What about forging? Who knows what forging is?
Heating up a piece of material and like kind of like pressing and stretching it.
Yeah, so that's true. You heat the material, and then you deform it, you change the shape with force and pressure. Right? A lot of times that could be as simple as a blacksmith hammer, or it could be as complex as a 50-ton hydraulic press or 500-ton hydraulic press, depending on the size. What about pressing?
Press it.
Okay. Yeah. So pressing, punching,
Oh, like a brake press?
yeah, well, yeah, brake presses, sheet metal dies that maybe just have a one hit and
Oh, stampers. Stuff.
yeah,
Okay.
yeah, all that all is going to fall into that, primarily sheet metal type stuff. And what about extrusion? Everybody familiar with extrusion?
And it's just taking it like a sheet or a piece and stretching it like
Yeah,
a straw through this and poking it out.
yeah, that's what it is. So, and that's an amazing process if you've never seen it. I'm probably going to have to show videos. I'm sorry, that's probably going to take up our time, but I'm probably going to have to show some videos. We all had as children probably this the Play-Doh set where you shove the Play-Doh into the little lever and you put the little slide that makes the stars or the spaghetti shapes, and you squish it and the Play-Doh comes out those holes at that shape, right? What's that? It wasn't what?
I wasn't that low.
You didn't have Play-Doh?
No.
Are you kidding me?
I got a bowl of flour.
Oh, you had the homemade Play-Doh.
Yeah.
Okay. Well, I can understand. So you didn't have the little press thing.
Yeah.
Well, you could have probably found one.
You could have squished it.
Well, okay. Well, that's sad. You're the first person, Parker, that couldn't relate to the Play-Doh press.
But I know what Play-Doh is.
Yeah, you can visualize what I'm talking about. Your buddy's probably had one, right?
I was a middle child.
Yeah. Okay. Well, your older brother definitely had one, or your
Yeah.
older sibling. Yeah. So, but that's the extrusion process. You actually are forcing material through a die of a certain shape, and it comes out, in links. So you guys are starting your venture into solid modeling with Inventor. What's that main process called that you use to make your solid shapes?
Oh, yeah.
Extrude, right? So what's that mean? You draw a 2D shape and you give it thickness. That's extrusion. Powder metallurgy. Has anybody ever heard of that?
Yeah, that's your powder coat, isn't it?
Not exactly. So powder coating is a surface finish, but powder metallurgy is when we're taking these materials in a dry powder, individual molecule or particle size, and we apply heat and pressure, and it centers those molecules into a shape. It's kind of like casting, but with dry powder. Okay, so anyway, we'll get into that. But why those manufacturing processes are important is because each of them may have additional information that needs to be on a drawing. So a lot of times you will see on parts that are cast, you'll see things that maybe you don't see on other drawings. So if you're looking at this drawing right here, what's some stuff that might seem a little foreign? Now we mentioned the check boxes, but what's some other stuff that maybe you don't quite wrap your mind around just yet?
I mean, you got a little legend down here,
Yeah, we got this stuff and this stuff and this stuff and this thing and this over here is all GDT. So I'm going to save that for later. So let's ignore that. What else outside of those things do you see?
what about a cord hole,
Cord hole. What do you think that means?
like you're drilling a hole.
Okay, sort of. You're making a hole, but when you core it, that means you're putting a chunk of material in the cavity of the mold before the material gets in there, and the material goes around that. So it's a core placed in the cavity. So that's
So like strengthen the screw area or something.
well, it just keeps you from having the material in there to have to drill it out.
Oh,
So it just saves on material waste and faster time curing and all that
Spacer.
stuff. Yeah, so it's actually just a block placed in there that makes a void right there. So that's a core.
oh, it
It's
comes
like
out.
whenever
Yeah,
you
yeah.
cast it,
What's that?
whenever you cast it.
Yeah. So in the cast, which a lot of times is sand, and maybe if I show my videos, we'll show that. I got a little bit of aged one, but it's pretty cool. But you put this block, in this case, it would be a cylinder that's going to make a void there of a hole, a 1.5 inch diameter hole. So core. So put it in there and cast around it, and then it comes out after the casting's done. So that's definitely something new that you hadn't seen. Anything else jumping out at you?
Casting size allowance provided for machine.
Yep. So that's a big thing. And there's two more things I want to point out, and then we'll kind of get down in the weeds with what it's talking about. So we have this note here, parting line. Okay. So that's where the two halves of the mold separate. And if you have anything that's injection molded or even cast, if you look at it really closely, you'll see a seam all the way around it. And that's where those two halves of the mold meet, and that's called the parting line. So along with the parting line, we'll also see these notes about draft angles. So everything that's cast, all castings, all injection molded parts, all things that material goes into a cavity and has to come out, include these draft angles. These draft angles help the part come out of that cavity once it's finished. If it's straight 90-degree edges, the part gets stuck in there.
Yeah,
So those slight angles allow those things to come out. And if you guys hadn't seen this little doodad back here, but this is an injection molded thing, and maybe I'm getting a little bit ahead of myself, but so the blue is one half of the mold, and the green's another half. Cope and drag is what they're called. They open, right? Separate open like this with a machine. This one has a special slide because it's making a hole. So parting line, right? Parting line. And anytime you have a hole that's perpendicular to the parting line, you can just put that hole in the mold and it molds and everybody's happy, right? But if you have a hole that's parallel, the axis of the hole is parallel to the parting line, then you have to do some magic in the mold to make a slide come over there and lock in and make a hole. But that's a little bit more expensive, a little bit more challenging. But that's what the red piece is, a little slide that as the mold opens, the slide comes up. As it closes, it goes down. And then you squirt the material into what's called a gate right here. Material goes in, squirts up, and then when it's done, it opens. As it opens, again, the slide comes up, and then ejector pins push the doodad out. Okay, so if you have, look, if you've got any toys at home still, primarily toys, you can see it really easy, cheap plastic toys. You look at it close, you will see, and you can get this thing and look at it here in a minute, I'll pass it around. You can see the parting line usually. You can see where the gate was broken off and maybe sanded a little bit. You can see a little spot where the material came in. So this is called a sprue, and that gets cut off and sanded and thrown away or recycled. But every injection molded piece will have that. You can see what's called the gate where the material comes in. You'll see the parting lines. And if you look really close, you'll see those little circles here, there, and yonder. And that's where those ejector pins hit that part while it's still a little bit soft and push it out. So you'll see that on every one of the injection molded parts. I got sidetracked with injection molding when we're talking about casting. I'm sorry. I get kind of passionate about this stuff because I think it's cool.
We have, I know there's one or two shops in the
Oh, yeah.
area, but do we have several mold injection shops?
I think so. I think Arkansas Tool and Die is up there looking for some SolidWorks people right now. So I think that's what they do. Big part of what they do. All right, but back to casting. Draft angles. Everybody understands that draft angle is to help that part release from that mold as it separates. There's interior draft angles and there's exterior draft angles. Yeah.
Is that like, is there a formula where it's already done, or you just typically go a couple of degrees and you're good?
It's usually a very small amount, and here's kind of where I want us to be at the end of this class. You know, determining what those draft angles should be is an engineer's role. I mean, it really is. But you go to work for somebody that does castings, and they're going to take this existing casting that they got, they're going to make it a little bit smaller here, a little bit bigger there, and you're probably just going to reuse the historical knowledge that they found successful with draft angles to that new part. You know, so I'm not saying you won't deal with draft angles, but you'll probably be in a place that there's a lot of historical knowledge about what works and what doesn't, and you just keep using that. So I don't want to get down in the weeds and trying to, it's above the scope of my knowledge, but an engineer is doing that. So what I need you to understand is what that really means. So here's the parting line. So an external draft angle is going to, you know, this wall, and this phantom line is the size of the material when it comes out of the casting. I cannot cast these threads, these counterbore holes. I can't cast those with any dimensional accuracy or precision at all in a casting. Okay. So what I do is I cast this block that is the shape that's outlined by those phantom lines. And then I take it to a CNC lathe or mill, and I'm going to turn this part. In this case, it'd probably be a lathe. I'm going to turn this part down, cut these threads, bore out this hole the right size, and have a finished part. So the phantom line is what comes out of the casting. But back to draft angle. So, you know, this line here would be an external edge, right? This line over here would be an external edge. Does that make sense? What we're calling external. So what that truly means is that this line is probably, you know, 91 degrees instead of 90. So it's 1 degree inward so that it can come out of the casting. This is a cord hole, so it probably doesn't have draft angles because the cord can come out pretty easy. There's really not any interior angles in this one. But if this was like a cast hole, then this hole would, maybe not a hole, it's not a good to say, but if it notched in, if say this just came in and notched right here, then this would have a 2 degree angle right there, so that this plug that comes in to make that hole or make that little notch could retract out of it. So it's just important that you understand where the interior angles and where the exterior angles are at. Now, here's the question I get all the time when I make these drawings. Do I need to draw those angles? And at this point in our life, I'm going to say no. Just draw them 90 degrees, put the note in there. Okay. Model them with Inventor with 90 degrees. Inventor's got some tools where you can add draft real easy. And most of the time, if somebody is making the mold, they'll take that model and they'll run a draft analysis on it. And the software can figure out those drafts really well too. So yeah, so maybe we'll get into that some. But the software will kind of run that draft analysis and tell you where there's issues at and help you guide to fix that. So what I want you to do is to draw them 90 degrees, but this is a very important note that needs to be on your work. Okay, so we're adding that to our notes of stuff to put in there. And remember, our notes go over here in this, our general notes that talk about the whole part on the whole drawing go in that lower right-hand area near the title block. I've been seeing some like over here and up here. Let's just get in the habit of putting them right down here somewhere. All right. So parting line, external angles, casting allowance. So where you see that casting allowance sticking out, you also see these symbols here, and I'm getting a little bit ahead of myself, but those are surface texture symbols, and those are achieved by machining. So I take that block of casting out of the sand foundry area, and I transport it over to my machine shop area, and now I'm going to remove this material to achieve a certain level of finish. So I don't want to get too far ahead of myself, but that's what that's saying. I want this to be so smooth. And this 0.06 right here, and we'll get to that in just a second, is how much extra material has been cast to give you room to machine to get that surface. So that's how wide that phantom line gap is away from your original part. So this is a pretty good example showing all that. There's a lot going on with this drawing. There's new stuff for us. But right now, I just want you to understand chord, parting line, external, internal draft angles, more important notes, and then this phantom line dictating where the casting was at. All right. So I should have went to here. So here's the interior and interior exterior draft angles. So I think I've hit this, but does everybody understand the difference between interior and exterior draft angles?
Yeah.
Okay. So here's a forging part, very similar to casting. Remember forging, we heat this part up and then we deform it by extreme pressure, you know, whether that's a hammer or a press or what have you. Some things that are consistent, and I didn't mention this before, but we also are going to have rounds and fillets. That's why you're seeing that note on a lot of your drawings. So all these corners are rounded, you know, and this one's even got a bigger fillet that's noted a little bit larger, but all these corners right here have those rounds and fillets, and that's to allow for proper cooling. So it cools at a more uniform rate. If there's a sharp corner there, the very tip of that corner is going to cool a lot faster, and it'll cause some imperfections and quality issues with cracking and stuff like that. So that's why all your cast parts, injection molded parts, and forged parts will have, rounded corners. Rounded corners. And again, it's helping get it out of the cavity too. Forged parts also have draft angles. They're usually a little bit more extreme. Notice these are 7 degrees draft angle, and it's both interior and exterior. And some of the interior ones have been leveled up to even 10 degrees. So you can see that on the drawing there. There's still a parting line. So in this case, not all castings or forgings have a 2-part cavity. It could just be a 1-part, but there's still a parting line where it hits the flat base. So you can always see that seam. And the draft angles happen from that seam outward. So what I'm saying is, you know, here's the parting line. So going this way, it drafts this way, right? And going up, it drafts the opposite way. And again, that's to help it release from that that cavity. You know, we have some other tolerances here. So we're trying to keep the thickness uniform within this range. Mismatch is kind of like if you've seen some cheap cast tools or forged tools, you might see a little flash or a little, you know, a more protruding edge along that parting line. Some, you know, that's where the two halves are a little bit off center from one another and kind of gets a little wonky. Maybe some cheap die cast toys, you might see that on, or stuff like that. A little bit of misalignment. So I think that's pretty much the stuff there. Then we take that forged blank and we take it over to the machine shop. And again, you're seeing these things here, which are indicating that we are removing material, and it's going to be a certain smoothness value. We're getting there. We're getting there. Trust me, we're getting there. All right, so we also can remove process material. Yeah.
When you're given the drawing and you, I mean, most of the time it's the crude drawing,
Yeah.
and you've got creative. Are they taking into account that overage that's gotta be like? I'm trying to think, because you've got that 6,000, like on that
Yeah.
one picture that we're gonna machine up.
Yeah.
Like, we're drawing all of that, including the stuff that needs to be taken off, correct?
Yeah, so your finished part drawing will be the final shape, and you would include a note that indicated how much overcast was made on it. In
So
the
it'll
symbol.
be the finished product,
Yeah.
showing notes that it should be
Yeah,
a little bigger.
that the casting has this much of material allowance at this particular spot. That's a good question, and it's coming.
Okay.
It's coming. Back to processes. So the other one was reshaping material. This is removing material. A lot of these processes you're familiar with: drilling and reaming, boring. So drilling, we've all probably drilled some holes. Everybody drill a hole? Parker, did you have a drill growing up? Good deal.
Kind of drill press.
Oh, cool.
Hey, that beats a Play-Doh set. any day.
Yeah, I'd rather have a drill press as a Play-Doh press any day. Yeah, that's the way to go. So, has anybody heard the term reaming? I mean, you've seen it on the final project and in Intro to CAD, if you remember, computer engineering graphics. But what does it mean?
That where you're planing it out or whatever.
It really is. So a ream is a special precision tool to get very precise holes. So your standard drill off the shelf has got some rough tolerances, right? So if you really need a precision hole, then you would pre-drill a hole and then ream that hole to the precise size. So you'd pre-drill it undersized, and then the reams are only designed to cut a small variation. So usually they're paired with a certain drill, and then that ream would take out the rest of the material to a very precise size. Another process, but it's the same similar tool, but a much more precise tool. Usually doesn't have a point on it because it has to go through a hole that's already there. So they're usually flats. What about boring? What's the difference between boring and drilling? Anybody know?
Get that out.
Yeah.
Boring, like, hitting the wall of the.
Yeah. I think you're on the right track. So boring is there's already a hole there, and you're going into the hole with a tool and removing material inside an existing hole. But it's usually on a lathe, and it's a 1-tooth tool versus the ream that has a whole diameter. So the individual tooth on a lathe will clean that hole out on a boring process. So, you have an existing hole, and then you have a boring bar that kind of comes in and removes a little bit more material in that hole. So you can't start a hole with a boring process. You have to finish. Again, it's a finishing hole to a precise size. And the advantage to this on a lathe versus a ream, for every precise hole size, you have to have a special ream tool for the reaming process. For this lathe, you just have to have a boring bar that'll fit in that hole. So you can make a wider variety of sizes with one tool. The kicker is always going to be the diameter of your tool holder, the boring bar. Will it fit in the hole? And then if they get really small, then rigidity becomes an issue. Lots of variations. But anyway, those are the difference between that. Turning and milling, you're familiar with those processes?
Yeah.
Yeah, everybody? Cool. Just a little bit. We'll watch a video. I think I'm going to make you watch videos. I was hoping to keep this short, give you plenty of time to work, but y'all just have to work on your own time somewhere.
You're all about these videos.
Yeah, I think it's gonna be good stuff. It really is. Yeah. So just kind of the primary difference between milling and turning. They're both, material removing processes, common in machine shops. Turning, the material is going to be round bars, and in the turning process, the bar is spinning and the cutting tool is stationary and engages the spinning bar. In milling, it could be, rectangular bars, square bars, round bars, any shape. The material is stationary and the cutting tool is turning. Most milling operations are what's called vertical mills, but there are some horizontal milling centers and stuff like that. So just if you think of it in terms of, is the tool spinning or is the material spinning, that'll usually get you in the right game if you need to know which one's which. Broaching. So anybody heard the term broaching, know what to do? We talked about this a little bit the other day. What's that?
I've heard of it before, and I used to use it at my old school, but I forgot what it was.
You did some broaching? Okay, cool. So broaching is typically a process that uses a press type machine to cut keyways into a hub. This is the primary purpose. So the cutting tool's got a lot of mean looking teeth, and it's just like a big arbor press that broaches through there and cuts through those keyways. Shaping and grinding. This is not there's a tool called a shaper, and I'm going to lump these two together. This is not your bench grinder that you're thinking of, or your angle grinder that you may have in the garage. These are very precise tools, and they're both very similar. So the material will fit on a magnetic base, and the base travels very precisely in uniform strokes to an abrasive, and it takes it to a very, very high precision finish, both smoothness and dimensional tolerances. So
They've got a like 500-year-old one that custom.
yeah,
This is a big old stone wheel, and it looks like it's from like the early 90s, like one of the first ones ever made.
yeah, and it's
that
probably
sucker sits there all day, just
just
leveling
going back and
the
forth. Yeah.
material
These other processes I've not really seen, super finishing, chemical milling, explosive forming, electric, just EDM. I have, seen some of it
There's some
going
cool
on.
videos on that explosive form stuff.
I haven't watched those, and I don't have those in my library, so I may have to search those out.
Pretty cool stuff.
But those are all using science to remove material. Okay. Electron distraught machining actually removes a very small amount of material by what it says there, discharging electrons, just knocking the chips away. And it's really for intricate, really fine detail or interior details on a die where you really can't get a cutting tool in there. The workpiece is typically submerged into a liquid, and I'm not exactly sure what the liquid is, but the torch tip would go down into the liquid, and the electric discharge happens to just kind of keep everything controlled inside that liquid. Really cool process and really intricate. So some of these that we might be familiar with if we're talking about adding material would be welding. Plating would be, powder coating, like you mentioned before, would be in that plating scenario, or nickel plating, or any type of plating where we're trying to control the corrosion resistance. I came from a background where we did a lot of brass plating on steel wire. So brass is just simply copper and tin. So put those two together, you make brass. It's pretty cool. Coating, paint, Flex Seal, whatever.
Old flicks.
Yeah, preferred hole sizes. It's not really going to come into play for us too much, but there are some basics of preferred hole sizes, and this kind of goes through the standard tooling available. We're going to make the holes whatever the project says. So
This is more of an engineering
it
call.
yeah, it kind of is. I'm not gonna say pick a hole for this. I might give you the size hole and tell you what the fit needs to be, and you figure that out. But we're not going to be designing hole sizes. So we've already beat this horse last week. I don't even want to get into it again unless y'all just really do. But we understand clearance has that C at that second digit. We understand that interference has that N. So LN and FN are interference, and that T is transition. So we didn't really talk about the metric ones, so I will spend a minute here. A lot of times when you're drawing, you might see, this diameter, and it might just be a hole, and it says diameter, capital H9. Or maybe you're looking at a shaft and it gives a diameter and it has this little D9. So the capital letter is the hole and the lowercase letter is the shaft. And this just happens to be H and D. There's other letters in the game. Okay. These are probably the more common ones you'll see. So, you know, these combinations of the capital letter and the lowercase letter are the same thing to give the same types of fits we've talked about with the inches, okay? But the metric system just gives you what the hole should be and what the shaft should be, and the combination of the two together defines the type of fit. But a lot of times you're just working on one part that maybe just has the holes and you don't even see the shaft and the stuff that we're doing here, right? You would just have a hole that has H9 or a hole that has H8 or H7. But they're really intended to give you those pre-engineered fits, just like the inch stuff. What makes it much nicer is they just give you this nice table that just gives you the answers. You don't have to do the math. You don't have to do anything, right? Yeah, I don't know. So here's the thing. Just like in the inch table, you have to find the appropriate row of data by using that column that says up to and including and up to. So it's got a range of numbers, and then you find the row, and then you go over to the right column. So if you've got a hole that says 40 H9, and you'll look through the tables and there'll be, you know, H9s on every page. They're all the same. It doesn't matter which one you get. You just find the capital H9, you go down to 40, and the numbers are going to be the same. Those are just different fits on the different pages to try to help you understand the fits of how the uppercase and lowercase go together. So here you see them both together. You see that the capital H9 for the hole and the lowercase D9 for the, and over here it's describing the fit. So maximum clearance, right? Minimum clearance. That makes sense. But you don't have to worry about that. So it's 40, and you just, here's the lower limits 40, 0, and upper limits 40.062. That's your numbers. Just put those in and rock and roll. What if you get a 39? 39 H9. The table doesn't have 39 in there. The next one maybe is 30, up to and including 30. What do? You don't know?
Just track the fit.
So, yeah. So you just change this number from 40 to 39. If it's 35, you go to 35. But you have to make sure you're in the right row because it's up to and including that number. So you can't go back. You know, if you had a 29 H9, you couldn't use the 30 row. You have to use the previous row. I'll try. I think there's a table maybe coming up. But you just get the numbers off there. There's not, but I'll look at the metric one here in a second. Now we're going to talk about those little triangles. Told you it was coming. Here it comes. So if we take a really close look, and it kind of goes back to the measuring stuff we talked about the other day, you know, if you're measuring with a tape measure versus a micrometer, you get a much more precise measurement and a much closer look at what's really going on. So if we take a really microscopic level of these surfaces, we can see these irregularities that are kind of shown down there in the image. And what we're trying to do is we're trying to specify the amount of that irregular surface variation that we can have. And we're going to call that roughness height value, which is the average of the deviation in micro inches or micrometers, you know, along that line that's kind of outlined through the center of those peaks and valleys. So it's just the average of those peaks and valleys. And the smaller that number is, the smoother our surface is, right? There's a lot of things that you can control with the surface texture symbol, roughness spacing. That's the parallel distance between those surfaces, so the successive peaks. We're not going to get too down in the weeds with this. So our symbol can have all of this different stuff on it. Okay. I want us to understand this one, and this one, maybe. Those are probably the only three that's going to come into play for us. We're not going to do any of this in this any of the artwork here. So we need to understand roughness height value and where it goes, which is right at the end of the check mark. You may have seen some of those already that had a number right there where A's at. Machining allowance. What is that? What is that? That's that extra we cast into that part that we saw a while ago. How much extra? Well, we put that number right here in E.
That's right.
Yeah, that's where that phantom line was at. That's where that phantom, that's how far off the edge that's finished where that phantom line's at. And then the lay, if you look closely at machine parts, a lot of times you can see the tool marks left over on the cutting tool. And that gives a distinct pattern on how, which way the tool is going and all this and that. So sometimes you might want to control that left behind pattern that you see on there. So you'll see this symbol just like this. And it doesn't give the roughness height value, but that symbol like that without a roughness height value doesn't give any value. So on your drawing, if you put the symbol in like this, somewhere on your drawing, there needs to be a note that says, where indicated, surfaces 63 microns. Maybe you got 50 of these check marks and you don't want to put 63 on there 50 times. You just put a check mark there and you got a general note, where indicated, surface finish 63 microns. Right? So, this is, you could put it on there. This is an older method. We're not going to do any ends. But 63, it doesn't have any units of measure on there. It's just a number. So the unit of measures are always known. If it's an inch drawing, it's going to be micro inches. If it's a millimeter drawing, it's micrometers. You don't have to put any symbols there or anything, just the number. And that number is representing how smooth it is. Now, there might be a tolerance range of surface texture, just like everything else. As long as that surface was in that range with no rougher than 63, but I don't really want it any smoother than 32. So that's a tolerance for that roughness height value. You might see it that way. And if we put the lay symbol in here right now, we don't know what that means, but I think the next slide is going to take us there. But that's those tool marks that you'll see. So the lay is the predominant surface left behind by the tool marks. Flaws are just irregularities that you really can't control. But here's some of the lay tool marks, and you've probably seen some of these if you look close. So parallel means the lines are parallel to the surface. Perpendicular, they're perpendicular to the surface. Maybe it's got an X pattern. Maybe it's multi-directional, circular, radial. You can always refer back to this table if you're not sure, but there's not going to be a lot of these, if even any. I don't know if I got any projects, but I do think it's something that you may encounter. Questions so far? So you'll see this symbol kind of has three flavors. So this is the most basic symbol. And when you see that, you're saying, I need a surface texture value of such and such. And I don't really care how you get there. I just need it to be smooth. This one with the line across the top of the check means I need a certain surface texture smoothness level, and you have to remove material. You have to machine some material off there. Why? Primarily because I've cast an extra 60 thousandths on there for you, and you have to come back and remove it. So that means you have to remove material. Mandatory, because I cast extra stuff in there. Does that make sense? So this is what you would see with that machining allowance of 2, means there's 2 millimeters extra cast on there that you have to take off. And then when you take it off, leave me that surface smoothness that I need. The other one has the little circle in it. And it says, hey, look, I need you to get the surface texture smoothness level, but you can't take any material off. You can't, there's nothing extra there for you to get. You gotta find a way to get that smoothness out of the box. If it's injection molding or casting, then you have to do a lot of prep in that area of the mold or casting to achieve that surface texture right out of the block. Prohibited machining. Maybe there's You know, up at Danfoss, they do hydraulic valves and blocks and things, and they have all these little tunnels and paths for the hydraulic fluid to go through, and they know they can't get that wall thickness any thinner. So they would prohibit machining in a certain area so that they ensure that that wall thickness is maintained between those voids for the hydraulic fluids at, 10,000 PSI. They have enough material there to hold that pressure. So it's really important. How do we draw this thing? And this will be in Canvas. If it's not already, I'll make sure it's available to you. And for the life of me, I don't know why AutoCAD doesn't just have a surface texture symbol, but it doesn't. No big deal. I can draw lines in AutoCAD, right? So here's the size the surface texture symbol should be. We're going to use X as 0.09. So that's the size, that's 3/32 of an inch. That's the size of the text that I want your 2s or your 63s to be in those places for A or B, on the symbol. Now, that's printed paper size. So if you're working at a scale, either you're using annotative, and all this stuff is printed paper sizes, so you have to account for the scale to get your stuff right. In Inventor, I think the symbol is going to come in much larger than this. So if you're, how close are y'all getting your Inventor legs under you?
Pretty
good.
Are you making drawings yet in dimensions?
Oh, yeah.
Okay, well, this may be the time because Inventor does have a surface texture symbol, and you just pop the numbers in and it pops it right in. So if you can make drawings in Inventor with dimension, actual paper, print out drawings with top view, front view, right side view with dimensions, you're doing that?
Yeah,
Okay.
we started.
Yeah, you should be at this point in time. So whenever you want to make that migration, Christian, I know you worked through that book through the ice storm, right? And you're ready to. Maybe not. You can draw them in AutoCAD, no big deal. But here's the lines. And so the height of that check mark needs to be 1.5 times 0.09. And the height of the long leg would be, 3 times 0.09. And they're on 60-degree angles. So it's not too hard to draw. And just, you can rough the text in there about where it belongs, as given on the symbol here, just roughly right there. Doesn't have to be precisely any certain spot, but have to manually draw that doodad. So which one is the lay symbol? Everybody agree it's D? All right, how do we put these check marks on our drawings? Different ways. And there's a preference in how to apply these. And this is real critical to doing well on these first drawings, is trying to put these things right and really understand where they're at is controlling what surfaces we're finishing. So you really want to have in your mind really clear what that edge represents on the drawing. So if you're looking at the view, you know what edges we have where. So the preferred place is going to be to put them on extension lines. And usually you have dimensions already there. So you put those surface textures on the extensions that represent the surface that you're trying to control. So in this case, this extension is coming off this line right here, right? So what we're actually trying to control is the round surface on the very end. That's the surface that's being smooth. Does that make sense? Everybody get that? So let's look at another one here. So, the extension line is this edge, right? Which that edge is representing this entire cylindrical surface. That's the surface you're trying to control with that edge. Does that make sense? All right. So this one is coming off this hidden line, which you guys are not going to do that, right? Never all caps. Anybody seen that yet? Never in all caps. That means I'm yelling. So what that is controlling is this edge right here, even though it's done poorly, which is again the bottom of that little pocket, right? Does everybody kind of wrap their mind around what that is? Okay. What about this one? So this one is pointing to this edge of the hole. So that's talking about the surface inside of the hole, all the way inside, the whole interior of that cylinder of that hole. All right, so very first try to put them on your extension lines. And they're usually, if you had, if you had this diameter dimension out here or something like that, they might be up there closer to the par. They might, they're usually not. Don't put them like right on top of the arrows. They're usually between the part and the arrow, and not in line with any of the other lower arrows if at all possible. Just kind of keep the confusion down. The second part might be to apply them directly on the surface or attach them to a leader that's pointing to the surface. So if we look at this leader here pointing toward this surface, that tolerance of 0.8 to 1.6 is this whole smooth, part of that shaft right there. And that's the biggest thing, is being able to look at the problem and understanding which surface so you get it on the right extension line. Because most of the time though, you'll get a 3D view and it's just pointing to that surface and it says, sometimes they got them on the extension line already, which is nice. And then, so, kind of back to it. Extension line is the preferred place, directly on the part, and then like the last case scenario, you can use a leader. Kind of work it that way if you can. So which one is the roughness height value? A. All right, good. What does this one mean? Gotta take material off, right? Obligatory. That's a hard word for me to say. Obligatory. All right, surface textures. Used to have a little doodad in here. Cleaned out. I didn't clean this drawer, so it should still be here. I don't know. I'm gonna have to find it. It's up there. I got one right here somewhere. All right. So surface textures, we're trying to control how smooth that is. Why do we want to, what would be a purpose to control how smooth something is? There's really two reasons, I think. Movement, right? So to reduce friction while things are moving, right? And the other is to kind of also control wear, which they're both kind of the same. So, we understand the symbol. We know what we're looking at there. Preferred values. Here's where I want to get to. So this is a process chart with some, typical surface finishes based on those processes. So kind of the average person running this, let's just do sawing, right? So the average person running a saw can probably achieve a surface texture within this range right here, up to 250 micro inches, 6.3 microns. So pretty coarse, but the average person can saw within that range without any issues on a regular saw. An expert can get into this other range, maybe. A highly skilled person running that equipment could probably get past that average bar on the black. So you can get into this, highly skilled operator can get into this range with well-tuned equipment. But, and then here's why all these other different processes exist. So if we talk about drilling, we can really only drill and expect to get to this range, right? But if I'm going to broach ream, then I can get a little bit smoother. And if I'm going to bore, I can get even more smoother, right? Does that make sense? So these are just your average expectation range and surfaces per process. So I think we beat this drawing down. I think we beat that drawing down. All right. So questions about that stuff?